Largest stars ever discovered. Our Sun is pretty big. It's so big that about 1 million Earths could fit inside. But how does our life-sustaining ball of plasma compare to some of the giants out there? When you start to think about it, the scale of it all becomes almost incomprehensible. Some stars are 1,000 times larger than our Sun. But before we begin, please like and subscribe to our YouTube channel for such amazing and informative videos. Others are millions of times larger, and the biggest are nearly 10 billion times larger than a Sun that's already 1 million times the size of our pale blue dot black small square. Welcome back to Phenomenal. Today, we're exploring some of the largest stars in the universe and whether or not they should even exist. Astronomers measure a star from its photosphere, or the outer surface of the star from which light is emitted. They compare the size of the star to our own Sun using a term called solar radii. So, if you have a star that measures 10 solar radii, that means 10 suns would line up neatly across its diameter. According to theoretical models, a star should max out at 1,500 solar radii. This is mind-numbingly large stars that have a big radius of around 648 million miles. If you compare by volume, 800 million suns could fit into a star that big. But we found a couple of stars that are even bigger. Up until recently, astronomers thought that the largest observed star was UY Scuti. UY Scuti is a part of the constellation Scutum in our Milky Way galaxy. It's not visible to the naked eye because it sits in a part of the galaxy whose stars are blocked by light from the Milky Waste core. But astronomers found it back in 1860. It has turned out to be very, very big, nearly 10,000 light-years away from Earth. UY Scuti was thought to have a solar radius of 1,700 with a margin of error of about 200. That means about 5 billion suns could fit inside it. UY Scuti has a circumference larger than the orbit of Jupiter around the Sun. It's so big that some hypothetical object traveling at the speed of light would take 7 hours to travel around it. If there was a planet orbiting Scuti, it would have to be over 600 astronomical units away from the massive Sun. 1 astronomical unit is the distance from Earth to our Sun, about 93 million miles. To put into perspective just how far 600 astronomical units is, Pluto is a mere 39 astronomical units away from the Sun. These stars have completely lost their hydrogen and emit about 10 suns worth of material. Every million years, as their cores collapse, they can either burst into supernovas or condense further into black holes depending on their masses. One of the most puzzling things about Stephenson 2-18 is its intense luminosity. It's 440,000 times brighter than the Sun. This is a number that was thought to be impossible based on the Eddington limit of luminosity, which is around 320,000 times that of our Sun. The Eddington limit is basically the maximum luminosity or brightness a star can achieve without bursting apart by balancing itself in a state of hydrostatic equilibrium between the outer force of its radiation and the inward force of its gravity. How can Stephenson 2-18 be so big and so bright? Somehow define the mathematical models of the universe before we answer that. Let's see how it could get so big in the first place. Stars are born from interstellar dust clouds that can be hundreds of light-years in diameter. At first, these clouds are cool and diffuse and consist mostly of hydrogen and helium. Over time, gravity pulls more and more atoms together within the cloud, adding to its mass. If a cloud becomes massive enough, it becomes unstable and undergoes gravitational collapse. As the cloud collapses, it gets hotter and hotter as hydrogen and helium atoms pack tighter together within the core of the cloud. More mass means more gravity, which sucks in more and more cosmic material in a process called accretion. A protostar begins forming. Cloud collapses usually result in hundreds to tens of thousands of stars forming almost simultaneously, creating embedded stellar clusters. Basically, a bunch of stars still surrounded by the remnants of their mother cloud. There are a few situations that can trigger the gravitational collapse that leads to the birth of stars. Helium and hydrogen aren't enough to collapse a cloud. There needs to be traces of other heavier elements. These can come from the remnants of older stars that have gone supernova and send shocked matter into the clouds at high speeds. The collision of entire galaxies produce enormous amounts of energy that trigger starburst formations as the gas clouds from each galaxy are squashed into each other. Jets from supermassive black holes have also been proposed as stimulating star formation, injecting energy into the stellar cloud and catalyzing its collapse. Whatever the cause, at a certain point, The atoms within the condensing cloud become so tightly compressed that they're stripped of their electrons, leaving highly charged ions with exposed nuclei. The rapid compression and super high temperatures of these exposed hydrogen and helium nuclei sets off nuclear fusion, which creates a star's fusion plasma generator. Once the star has stopped collapsing in on itself and nuclear fusion is humming within its core, the plasma of the star starts to expand. However, the expansion is counteracted by the star's own gravity and the plasma is pulled back. In hydrostatic equilibrium is achieved, which we mentioned earlier, where the star's gravity, its radiation pressure equalize. This results in a more or less stable star. Stars are then maintained by a continuous series of explosions as hydrogen is fused into helium. Our Sun fuses a remarkable 620 million tons of hydrogen into helium each second. But how does a star become a giant? One of the factors is the composition and size of the gas cloud that formed the star and the initial size of the protostar. Once a protostar has settled down, it becomes what's known as a main sequence star. These stars can range between 1/3 to 8 times the size of our Sun throughout a star's lifetime. It burns through hydrogen as it fuses into helium within its core. In some of the larger main sequence stars, this process is faster because they burn through their hydrogen faster. In smaller stars, it happens more slowly. It can take anywhere from a few million years to a few billion for a star to exhaust its hydrogen supply within its core. Once a star burns through its hydrogen supply, it's left with a bunch of helium. Helium takes a lot more energy and higher temperatures to fuse, which the star doesn't have. So the star begins to actually contract as its hydrostatic equilibrium is thrown off and gravity starts compressing in black small square. When it does, the core is heated up again. As more matter is pulled in black small square, additional hydrogen is sucked in towards the core and creates a shell around the helium center where fusion resumes. Then something called the mirror principle occurs as the inner core within the shell contracts. The layers outside the shell expand and the star becomes hundreds of times larger, meaning the core becomes hot enough to start fusing helium to carbon. When this happens, a massive amount of energy is released, ballooning the star into a red giant. This is what will eventually happen to our Sun. However, because the Sun is only a medium-sized star, it would balloon into a red giant, eject most of its gas, and then compress into a white dwarf. Stars that are at least 8 times the size of our Sun can undergo an additional stage where they become supergiants. Black small square. If they have enough mass, these large stars can begin fusing their carbon cores into even heavier elements like oxygen, sulfur and silicon, creating yet even more energy that powers a further expansion, creating some of the largest stars in the universe, stars like Stephenson 2 to 18. So how can a star like Stephenson 2 to 18 exist? If its luminosity and size seem to exceed the limits proposed through the mathematical equations of the Eddington luminosity limit and stellar evolutionary theory. The first answer is the simplest. We might have gotten the measurements wrong. Calculating the distance and luminosity of a star is pretty complicated. Determining a star's radius requires 2 initial observations: its angular diameter, which is how large it appears from Earth, and its actual distance from Earth. The angular diameter is easy enough to calculate, but determining precisely how far away a star is from Earth is actually very difficult. Interstellar radiation plays with the light from a star as it comes towards us. Also, many giant stars like UY Scuti and Stephenson 2 to 18 have variable fluctuating luminosity and expel huge amounts of gas, making them tough to see. The light from our own Milky Way galaxy also obscures many stars again, making them tough to see for nearby stars. Astronomers use what's called parallax to determine a star's distance from the Earth. Parallax. The same thing happens in the sky. Nearby stars seem to move faster across the sky over the course of a year by taking one measurement of a star's position and then another measurement 6 months later to calculate the star's distance based on its angle. But parallax measurements are only accurate up to a distance of about 400 light-years. For more distant stars, astronomers have used the spectral data of the stars. We can measure through parallax to figure out 2 elements that can help estimate a distant star solar radius: luminosity and temperature. Black small square nearby supergiants tend to have a lower temperature and a red hue. And astronomers take that data and project it onto more distant stars like Stephenson 2 to 18. In short, it's not the most perfectly accurate system, but it's still pretty effective. So, if the measurements are correct, our model of stellar evolution seems incomplete. The answers to why these supergiant stars are so luminous might have to do with a phenomenon called going super Eddington. Black small squared, the Eddington limit is the maximum luminosity a star can achieve while in a state of hydrostatic equilibrium. When there's a balance between its internal pressure radiating outward and the gravitational force pressing against it from the outside. If you remember, any star larger than 1500 solar radii should simply burst into a supernova. But Stephenson 2 to 18 with its 2150 solar radii hasn't. However, there are several ways the star can potentially go super Eddington and become even more luminous while still retaining its shape. The first is a theory called atmospheric porosity. It imagines an atmosphere around the star where there are dense regions surrounded by less dense regions. This would basically contain the mass loss of the star to the outer layers, producing more intense luminosity, while the denser inner core of the star remains intact. Another explanation has to do with what are called photon bubbles. Photon bubbles are radiation-driven instabilities in the stellar atmosphere. They are proposed to develop within a highly radiated star where the radiation pressure is higher than its internal gas pressure. Basically, these bubbles are capable of transporting photons, lights at faster, more efficient rates and allow massive stars to glow brighter. There's a whole lot of uncertainty regarding the largest stars in the universe for now. Stephenson 2 to 18 takes the cake. But as we develop better satellites and are able to look farther into the cosmos with more precision, there seems to be no limit to what we may find. Did you learn something new about largest stars ever discovered that you didn't know before? We hope you did. So, if you're interested in learning more amazing facts, make sure to subscribe to our YouTube channel and hit the bell icon to get notified by our new videos. Please like and share the video. Don't forget to comment down your views on this. Thanks for watching till the end.